Okay, so this morning we're going to talk about not the origin of the stars, but the origin of the entire universe, which is quite an exciting thing. However, we're going to have to go reasonably slowly because it's such a big idea and such an important one that we have to make sure that we get our evidence correct. So what we're going to have to do is build up to the idea very, very gradually so that you don't feel that I've just made it up. As a creation story, it's competing with a lot of things that you could argue are made up. And so the difference between the scientific evolution of the universe and any other version of the evolution of the universe and the origin of the universe is that the scientific one is underpinned by evidence. So we're going to go fairly slowly. It's going to take us 2 lessons to do this. Sit back, and if you want to ask me any questions at any point, please do. Okay, so although I said we're going to move on from stars, we are actually going to start with the stars. So you need to be aware of the fact that although a star is a very hot object with its core at millions of degrees, and its surface, the bit that the light's coming out of, for our sun is, I don't know, something like 3,000 to 5,000 degrees. Our sun's up probably nearer to 3,000 degrees. Just above the bit that's giving out the light is what's called the sun's corona, or the star's corona. It's a wispy layer of thin gases which are much more part of the coldness of space than they are the warmth of the star. And so when the light leaves the hot star, it has to pass through these cold gases that are lost lots of their energy to space. And because these cold gases are much cooler than the gases below that have given out the light, the cold gases are much more likely to absorb some of the starlight as it leaves the star. Now, what does absorb light mean for an atom? So if I can remind you that an atom has electrons orbiting the nucleus in shells, the shells are at different distances, and the electrons that are nearest the atom are the lowest energy electrons. And the electrons that are further away from the atom have more and more energy until eventually, when they have enough energy, they're capable of escaping from the atom altogether. So when we say that an atom absorbs light, what we actually mean is that a bit of light comes in and an electron uses it to take the energy from that little bit of light and become promoted to a higher energy level, an energy level that it wouldn't ordinarily exist in. Now, that means that the light that was leaving the star didn't get to leave the star and sail through space and be detected here on Earth. Now, just to complete the story, the atom can't stay with its electron in this promoted state. The electron will fall back down, and so it will emit the light again. It's just that it could emit the light in any direction, and it probably won't emit it in the same direction that it was heading in before. So again, whichever reason you want to look at, that little bit of light isn't going to make it to our detectors here on Earth. And we can detect the light here on Earth. We put a device called a spectroscope on the end of our telescopes, and it splits the light up into a spectrum, a bit like a prism does. I showed you that in class, but that was just a little lump of glass. A spectroscope really, really splits the light up and puts all the different colors in slightly different places. And what we see when we point our telescopes fitted with spectroscopes to the front of a telescope, what we get when we point them at the stars, is that there are colors that are missing from the spectrum. They show up as black bands. And the reason that they're missing is every single possible electron transition corresponds to a different frequency of light or a different wavelength of light. And that's because every atom, every element is unique with different energy levels, and the electrons can jump from, shell 1 to shell 2, shell 1 to shell 3, shell 2 to shell 3. There's all different transitions within each element, and all of those transitions are unique. They all absorb a certain frequency of light. And that's what you can see on this picture. And these are sometimes referred to as spectral fingerprints, because the light that goes missing from helium is different to the light that goes missing from oxygen. And that's different to the light that goes missing from all the elements on the periodic table. This pattern of bands is unique to each element. And there's a whole branch of science called spectroscopy that identifies elements by just looking at which bands of light are missing when we shine white light through them. Now, a star isn't made of a single element. It's made up of lots of elements. So when you look at the spectroscope images for an entire star, all of the elements of the periodic table will be layered on top of each other to produce an enormous number of missing bits of light, missing wavelengths of light. The staggering thing that we find is that when we point our telescopes fitted with spectroscopes at any star in our galaxy, in Andromeda, in the furthest away galaxies, no matter where we point our telescopes, we get the same pattern, like on your screen right now. Turns out all stars are pretty much the same, and chemistry works the same way across the entire universe, which we never really suspected it wouldn't be like that. It's nice to actually have some evidence, because science is nothing if not based upon its evidence. Some stars, the younger ones, the oldest ones, the ones that are maybe a first generation star, they do have much more emphasis on the lines for the hydrogen and helium, because they are mainly hydrogen and helium lines. And stars like our sun, which is almost certainly a third generation star, they have all of the lines for the heavier elements as well, because our sun contains the heavier elements on the periodic table. This is how we identify what stars are made of and which generation each star is by the different composition of its elements. So that's an interesting aside story, that we can do stellar chemistry using a telescope from here on Earth. But what's it got to do with our story about the origin of the universe? So I told a tiny little lie when I said that the pattern was identical. You see, the pattern is the same, but it moves to different places depending on what we're looking at. So when we look at the light that's coming out of some galaxies, let's take our galaxy, for instance, that's a good starting point, we see this pattern in the middle, which is the pattern that we also see in the laboratory here on Earth. If you take some cold oxygen and you shine white light through it, you can measure this pattern here on Earth. And when you point the telescopes and the spectroscopes at our sun, this is the pattern you see. In fact, if you pointed at any star in our galaxy, this is the pattern you see. But if we start pointing it at some of the galaxies, which are a little bit further away, an interesting thing happens. You get the same pattern, so like 2 lines, gap, 1 line, gap, 1 line, big gap, 3 lines, big gap, 2 lines. You get the same pattern, but it's all moved a little bit. So you can see that kind of these lines here, they're in the yellow, but when we point them at our telescopes and our spectroscopes at some galaxies, we find that the same two lines are actually shifted into the green. Or over here, we might find that the same ones have shifted towards the orange. This shift in the pattern towards the red end or the blue end is known as red shift and blue shift. We don't fundamentally believe that anything has happened differently to the elements in the star because the pattern is the same. What we think is going on is that something is happening to the light after it has left the star on its way through space to us. So the question is, what could possibly be happening that has changed the light while it's on its journey to Earth? And it's this question, what's happening to the light, that has led us to piece together, detective style, an origin story for the universe. So let's follow the light. It turns out that for a very long time, hundreds of years, we've known about this long before we started plugging spectroscopes into telescopes. We've known that you can do stuff to the wavelength of light and sound and water waves and any other waves you want to think about. It's not a light thing. It's not a space thing. It's called the Doppler shift, and you are familiar with it. So let me leave space for a second and borrow an ambulance. So you might have heard an ambulance drive past you in the street. Just have a little think for a second about that. And did you notice anything about it? The ambulance is a source of sound. You are the observer of the sound. And when the ambulance whizzes past you, or actually, if you're sitting in your car and you whiz past the stationary ambulance, it doesn't really matter whether you're moving or the ambulance is moving. Something weird happens to the sound waves. Just before I leave this slide, I just draw your attention to this box. If you want to open this PowerPoint up later, if any of you like your music, if you know what an a cappella group is, an a cappella group, this is an a cappella group on YouTube that sings science songs, and they've got a really nice one about the Doppler shift. But I'm not going to play that for you now because, like I said, my internet is not working quite so well as I'd like it. Okay, so let's have a look at the ambulance. There it goes. Okay, so here's the ambulance driving towards you. Look what happens to the waves. I play that for you a couple of times so that you can watch it. The ambulance is releasing the sound wave, but then the ambulance is also chasing its own sound wave, which means that when it releases each successive vibration, the peak in front of it is a little bit closer than it should be because it released it after having chased the previous one a little bit. Meanwhile, behind it, it's running away from its own waves, which means that the wavelengths, the peaks, are all spread out a little bit. I'll play you a sound of what that sounds like. I don't know if it'll work across the thing, but we'll see. I don't think it's going to work. Hang on. Did that come through? Did it play to you through my speakers? Oh, brilliant. Okay. I'll play it again then. So can you hear the pitch change? As it rushes towards you, you get quite a high pitch, but as it rushes away from you, suddenly the pitch drops. This isn't a space thing. This is just a waves thing. So if we have a little look at what that looks like, this is what the waves from a stationary ambulance would do as they propagate through the air. You remember these lines represent the peaks of the wave, and we're kind of looking from above the wave or to the side of the wave. So those are the peaks, or you can think of them for a longitudinal wave as the compressions of the wave. So air squashed together, air spread apart, air squashed together, air spread apart. Or you can think of it as peak, trough, compression, rarefaction, compression, rarefaction. However you want to think of it. The wavelength is the same all the way around the wavelength, as we've learnt about. But when the ambulance is chasing its own wave ahead of it, the wavelength becomes decreased simply because of the motion of the ambulance. It's chasing its own wave as it emits new peaks. It bunches the waves together. Likewise, behind it, the wavelength is artificially increased because the waves are being released further away from where they were supposed to be released if the ambulance was stationary. So as the ambulance rushes towards you, you hear these short wavelength, high frequency sound. But as the ambulance rushes away from you, you see this large frequency, low frequency sound. It's called the Doppler shift. And it has been known about for about 250 years. So this is a prime candidate for what's happening to the wavelength of the light. Could it be that the stars are moving? And it turns out, yeah, that's a really good explanation. There is some movement of the stars. We already spoke about the fact that the stars are orbiting the center of the galaxy. Well, that involves some movement, right? Well, it's not uniform, it's not perfect. And inside our galaxy, some of the stars are bumbling towards us a little bit, and some of them are bumbling away from us a little bit. We do get a slight red shift and a slight blue shift of the stars in our galaxy. But it's only a slight red shift and a slight blue shift. If we point at our telescopes at other galaxies, we get a slight blue shift from one side of the galaxy and a slight red shift from the other side of the galaxy. And this is because it's not just that spiral galaxies look like they're spiraling, they really are spiraling, like water down a plug hole. And this is our evidence that they are. So yeah, the Doppler shift is real in starlight, and it does show that the stars are moving about. The thing is, these red shifts and blue shifts are really small, and we can detect them and we can interpret them, but the kind of red shifts and blue shifts that I was talking about a couple of minutes ago are way bigger than we would expect from a Doppler shift. And that's not the only thing that's weird about them. 1925 was a big year in astronomy because Edwin Hubble had just got his hands on this brand shiny new telescope that had just been built in America. And he was using it to take measurements that nobody had ever taken before. And the measurements that he chose to use with this shiny new telescope, when he had his time on it, he might get an hour a day, but he was going to use it to the fullest. When he got his observing time on this new telescope, he decided that redshift was something he wanted to investigate. He started off by looking at the redshift of the stars inside our galaxy, and he found that they were pretty small, and some were red and some were blue, and this was exciting. It was good. It meant some of the stars were bumbling towards us and some away from us. A bit like, you know, the random motion of gas particles in a gas. And he was interested in that. But then he wanted to know about further and further and further. So he started pointing it at the other galaxies. not the edges of the galaxies to show a little bit of red and a little bit of blue for the spin. He was pointing it at the center of the galaxies to see, what's the average redshift or blue shift? Does it all cancel out because the galaxy is stationary relative to us, but just spinning? Or is the whole galaxy moving towards us or away from us? First one he pointed out was Andromeda, which is our nearest neighbor. And he discovered a slight average blue shift. Turns out that Andromeda and the Milky Way are actually heading towards each other a little bit. Now, it's going to be billions of years before they get anywhere near each other. But pretty much the Milky Way galaxy and the Andromeda galaxy have got so much mass and so much gravity that they're managing to reach out across this huge gulf of space. Remember, I told you 250,000 years for light to travel between the two. They are very far apart, but they're very close on a universal scale. And the amount of gravity that they've got is actually attracting the two galaxies together, and they are, in fact, drifting together. In billions of years' time, Andromeda and the Milky Way will collide, and one will tear through the other, and then over a period of a few more billion years, they'll settle down into one massive super galaxy. However, Andromeda was pretty much the only galaxy he found that was blue shifted. All of the others were red shifted. And as he ticked them off one by one by one, he started to get this slight tingling feeling that all the other galaxies are moving away from us. Why would this be? But again, not done with the weirdness. He then started plotting a graph of how fast they were moving away from us, which he was getting from the redshift and the Doppler shift, by how far away they were from us. So a little bit of redshift means a little bit of speed. A lot of redshift means a lot of speed. And he started plotting a graph. And that's the graph on your screen. It's not just that all the other galaxies are moving away from us. They're moving away from us with a speed that is directly proportional to their distance from us. How could a galaxy half the universe away possibly know how far away it is from us? And even if it did, how could it possibly tune its speed of motion through the universe to be perfectly matched to the distance from the Earth? And why is the Earth at the center of a cosmic explosion anyway? Why should every object in the universe be hurtling away from the Milky Way? Apart from Andromeda, which is a bit too close and has got gravitationally stuck to us. This is seriously weird data. You can interpret it, if you want to, that the Earth genuinely is, as promised in lots of creation stories, including the Christian Bible. You can interpret this, if you want to, genuinely, as the Earth really is the center of creation. But even if you do, you still have to explain why all the other galaxies are hurtling away from us and how their speed has been perfectly tuned to be directly proportional to their distance from us. It just doesn't make sense. It's a very, very good set of data to produce a very tight relationship. You could draw a line of best fit through that with ease. But there's no explanation there. It's Hubble's data that was the moment that we started thinking about the origin of the universe in a serious scientific way. So let's talk a little bit about cosmology. Remember, the cosmologists are the people that try to explain the universe. And they have to start somewhere, right? So the founding principle of cosmology is called the Cosmological Principle. And it basically says, in a nutshell, nowhere in the universe is special. Not even here. Not even because we're here. It basically says that no matter where you go, on average, It's about the same temperature. It's about the same density. They've got roughly the same elements in it. Yeah, there are some dense patches like galaxies and some less dense patches like the space between the galaxies. But if you pan out far enough on a truly universal distance scale, yeah, you see, like in this image, there are some bright bits and some dark bits, which is kind of like the galaxies and the gulfs between the galaxies. But pretty much, the universe is much of a muchness no matter where you go. Everywhere's kind of the same. And if I could invent some kind of transporting system where I just click my fingers and ping to random parts of the universe with my telescope, when I look up and point it at the sky, pretty much I'm going to see the same picture. A few stars, a few galaxies, blackness in between. Everything's going to look pretty much the same. It's called the Cosmological Principle. It's a good principle. It removes the Earth from the center of the creation story. And if we genuinely believe that our sun is an average sun in an average galaxy, and we're just a lump of rock orbiting this average star, if we genuinely believe that, then we have to accept that the cosmological principle is a good starting place for cosmology. Everywhere is pretty much the same. Which means, if we're pointing our telescopes at the sky here on Earth and seeing all the other galaxies zooming away from us, then if we were to use my magic click your fingers teleportation device and go to any other planet, anywhere in the universe, and take the same measurements, we'd have to see the same thing, and we'd have to conclude the same conclusion that all the galaxies are moving away from there as well. It's not just that all the galaxies are moving away from us. All the galaxies are moving away from each other. The entire universe must be spreading itself out. Now, I don't mean that you are getting bigger or the Earth is getting bigger. I don't even mean that the solar system's getting bigger. I don't even mean that the Milky Way galaxy is getting bigger. Gravity is managing to hang on to everything that it can do. It's even managing to hang on to the Andromeda galaxy. So we're not talking about little tiny distances that are getting bigger here. We're talking that the vast gulfs of empty space between the galaxies seems to be getting bigger. The galaxies themselves, unless they're near enough to each other to hold on to each other through gravity, the galaxies themselves seem to be spreading out. And not spreading out from anywhere in particular. They're just spreading out from each other. It's like each one is repelling all the other galaxies. Like they're all negatively charged or something, pushing each other away. Well, we know they're not negatively charged. We know they're neutral because they're all atoms. So what's going on? The mystery is just getting deeper and deeper. Why are all of the galaxies flying away from each other? How are they doing it? Craziness. That's what Hubble put out to the world in 1925. This is what I found. By appealing to the cosmological principle, this is what I think. Crazy or what? And someone read that with a very sinking heart. Because half the world away in Europe, Einstein sat reading that, slapping his head. Because 10 years earlier, Einstein had become the greatest genius on the planet, the most famous scientist on the planet, by publishing a theory of gravity and the universe, which he called the general theory of relativity. And before he published it, he had to fix a flaw in it. You see, his general theory of relativity predicted that no universe can stay static in size. His actual scientific theory predicted an expanding universe. But he dismissed it. Even Einstein, greatest scientist ever, greatest brain ever, just thought he'd made a mistake. No way is the universe expanding. The universe is eternal, infinite, timeless, the same forever. It's what people believed. Even Einstein thought he'd made a mistake. And so he took his beautiful, perfect theory and he added something to it to stop it predicting an expanding universe. And 10 years later, in the middle of the 1920s, over his breakfast, choking on his toast, Einstein referred to this as the biggest blunder of his life, that he hadn't trusted his science, his own equations, his own theory. He dismissed it. So it's Hubble that he is rightly attributed with the idea that the universe is getting bigger. Not Einstein, but it's Einstein that can explain it. The idea is that the universe isn't empty. It's not. It's got all this matter in it, and those big voids between the stars that we think of as empty, Einstein says it's not empty. It's a thing. It's a fabric. Einstein calls it space-time because it's the combination of space and time all bundled up together. It's the stage on which matter does its thing. When we say that stuff moves, it moves through and on and against space-time. It's like the piece of paper that we'd draw the cartoon of the universe on. But Einstein says it's not paper. It's a stretchy fabric, more like rubber than paper. And if we were to draw a grid on it, like a piece of graph paper, well, it's not graph paper, it's graph rubber. And what Einstein's saying is that space-time can't stay the same size. It has to stretch, or actually shrink, but we seem to be in a stretching version of it. The galaxies are capable of moving around on the grid, but just like if I put an ant on a rubber sheet and the ant can wander around on the sheet, the ant will also move across the room if I stretch the sheet. Even if the ant sits down and refuses to move, it will still move across the room that the sheet is in if I just stretch the sheet. So, sorry, that's a bit jerky, isn't it? Well, you have to play it back on your own computer later. What Einstein is suggesting, what his model predicted all those years ago, is that the galaxies aren't moving away from each other through space. They're moving away from each other on a space that is itself a rubbery fabric that is expanding. An expanding space-time. You are firmly at the end of a 4-year university degree in physics with this idea. You would need to go on and do a decade of postdoctoral studies after a PhD to fully get your head around the equations of general relativity and the predictions that they make. It is cutting edge science, 10, 15 years beyond school science. You got a lot of learning ahead of you if you want to understand this properly like Einstein did. But the basis of it is what I've just said. Think of space, the big emptiness between the galaxies, not as emptiness, not as nothingness, but as stretchy something that matter is kind of pinned to or embedded in. And this rubbery surface is being stretched. We'll come back to that in a second. But the galaxies are being thrust apart from each other Not because the galaxies are moving, but because space itself is stretching. Let's try and pin this down to Hubble's data. Imagine you've got 3 galaxies right now, today. There they are in the top picture. And those 3 galaxies are equally spaced from each other. So here's one in the middle, and there's 2 either side. So maybe this is the Milky Way in the middle, and this is Galaxy A in one direction, and a similar distance, Galaxy B in the other direction. Now, let's zip to a point in the future where the universe has doubled in size, that this stretchy fabric has been stretched so much that it's twice as big as it was before. So if we'd drawn a little grid on it, all the grid lines are now twice as far apart. This box that used to be this size is now twice its size. We've doubled the size of the universe. We haven't doubled the size of the galaxies because the gravity of all of the matter inside the galaxies has kept the whole galaxy together. It hasn't allowed space to stretch inside the galaxy. The gravity has kept the galaxy the same size, which is why in this picture, these images of the galaxy are the same size as this image of the galaxy. The galaxy hasn't got bigger, but the space between them has. Even if the galaxies weren't moving on space or in space or through space, space itself stretched. So what used to be this distance, which we can call x, has now become this distance, which is 2x. So it's a weird idea of speed because the galaxy didn't move through space. So if you were standing right next to the galaxy, you might look at it and go, you don't appear to be moving, because it's not moving through space. But we can still kind of use the idea of speed as distance over time. Those 2 galaxies were a distance x apart, x meters, and now they're 2x meters apart. A meter hasn't got stretched. A meter's still what it used to be. So if we start laying meter rulers together, we might be here for a very long time to measure the distance between the galaxies. But if we did, we'd get x meters between the galaxies once upon a time. And now we'd have to lay a whole load of new meter rulers to finish off the distance once space has stretched and moved the galaxies apart. So effectively, the galaxies are now 2x apart, which means an extra x. They're an extra x distance apart, an extra x meters. So speed is distance over time. Well, the galaxy is kind of moved on space a distance x in a time capital T. So if we knew what those numbers were, then the speed would be x over t, which is a number we can calculate. What about this galaxy? That one's further away than this one over here. So if we're the observer in this galaxy up here, we see this middle one moving away at a speed x over t. But Hubble says that this one should move away faster because it's further away. That's what the data says. How does that work? Well, that galaxy was originally 2x apart. And it's now 4x apart. So this time when we do speed over time, the change in distance is 4x take away 2x, which is 2x, not 1x. It's moved twice as far. But it did it in the same time. So this observer in this galaxy would see this observer, this galaxy, moving away at twice the speed that it sees this one moving away. If the expansion of the universe is the explanation for the Hubble data, then it includes this direct proportionality. It includes in it that double the distance will double the speed. It's really neat. And it's even neater because this idea was not invented to solve the Hubble problem. This idea already existed. Einstein had just put it in a box and wrapped it up and buried it so that it wasn't a real thing. But once Einstein recognized his mistake and took his equations for what they were originally, this is predicted. This was predicted before the experiment was done. It's really lovely when theory and experiment come together and reinforce each other. That said, though, I've given you the simplistic version of it, and I would like to, just because you're capable of doing it a little bit more properly. You see, it's not a Doppler shift. Doppler is when the galaxy moves through space. We should not be interpreting this as a Doppler shift, even though what I just said is really neat and tidy, and that, you know, if the galaxies were moving and on all the rest, it's nice and neat, but there's a neater way. We don't need the Doppler shift, because look what we can do with an expanding space. Let's think about the light that sets off from one galaxy to the other galaxy. In a static universe, it sets off and arrives exactly the same. But what if the space is stretching while it travels? Well, if that happens, then as the wave waves itself across space, the wave itself gets stretched. This stretching of the light does exactly the same thing. You travel through twice as much space, you get twice as much stretch. So we don't have to appeal to a Doppler shift. We don't need to turn the stretched wavelength into a speed and then talk about the speed being faster. We can just stretch the wavelength all on its own. No Doppler shift required. So we can interpret the redshift directly as a wave that is drawn on a piece of graph paper that is made of rubber, not paper. And that during our pen moving across the graph paper, drawing a wiggly line, somebody was grabbing hold of the rubbery graph paper and stretching it while we were drawing the wavy line with our pen. Which means that as we drew the wavy line across the paper, the rubbery paper, the pen was always playing catch up with the rubber that it was drawing on, meaning that the wave ends up being a stretched version of what we intended. Stretching out the wave makes its color change. A red wave has a longer wavelength than a blue one. You will still see in textbooks and revision guides and YouTube revision videos, and I kid you not, occasionally on your AQA exam papers, because your examiner, as I've told you many times, is not very good at some parts of the science. Not always. You will still see authors claiming that the redshift data is Doppler shifted. It is not true. There is a small amount of Doppler shift because the stars really are moving about inside the galaxies, and the galaxies really are spinning, and the galaxies really are a little bit moving through space. There is a little bit of Doppler shift. But those tiny little bits of Doppler shift are minute compared to the redshift that Hubble has presented. In fact, if we go back to Hubble's graph, which is somewhere around here, the reason that many of those dots are not perfectly on a straight line, partly it's experimental error, but partly it is that there is some Doppler shift going on. Some of those galaxies really are moving away and towards us through space, a tiny little bit. But the motions of the dots are kind of, from here to here. They're tiny, tiny little nudges that would be required to move these dots onto this line. The difference between a dot being here and a dot being down here, that's not a Doppler shift. That's an expansion of the universe, sometimes called a cosmological redshift, to get the point across that it's not a Doppler shift. But that's not going to stop it appearing in textbooks still, that authors who don't know their science very well will sometimes refer to it as a Doppler shift. It's nice to think of it as a Doppler shift, but ultimately the picture on your screen right now is the correct way to think of it, that the wave itself became stretched as the space it was traveling through stretched as it traveled. And if it had to travel twice as far, then it's going to be traveling through twice as much stretched space, and it's going to end up twice as stretched. And that's why there's a direct proportionality between the stretching of the light and the distance the light had to travel between the galaxies. Now, I promised you an origin of the universe story, but if you glance at the clock, our hour is up. So you're going to hang on to your seats until next lesson, when we will take Einstein's vision and Hubble's data of an expanding universe and ask, how can that lead us to a theory of the origin of the universe itself? But for today, that's where we're going to finish it.